morning. It's 10 a.m. so we can start. Today we're going to talk about electric power and then RC circuit problems. First, why do we use electric power? We discussed it in our lecture. Let me just quickly remind you. There are two main reasons. First, because it's easier to transport electric energy over long distances, right, with reasonably small losses, right? So it's a big reason. And the second, because usually in our everyday life we don't use electric energy directly. We use it in other forms, right? So every time we need to transform electric form of energy into other forms of energy, right? And it's easy to do it using electric energy. So you buy some electric device, right? I don't know, like a vacuum cleaner right there, right? You plug it in and it will transform electric form of energy using a vacuum cleaner, and it will transform into mechanical form of energy. Oh, there's a fan blowing some air at me, so feel better. Right? Again, it just transforms electric form of energy into mechanical, right? Or by heater transforms into heat, right? So every time we transform electric form of energy into any other forms of energy, whatever we need at that moment, right? So every time we transform, and of course the logical question, how much of energy do we transform, or can we transform? Right? And again, researchers went one step deeper. They don't just ask for amount of energy transformed. They ask for amount of energy per unit time transformed. And energy per unit time, that is power, right? So that's why I wrote power. It's energy per unit time, right? Amount of energy per unit time transformed from the electrical form of energy into other forms of energy. And so we did not derive, but we discussed. So there are three formulas which can be used. It's basically the same, right? You can use Ohm's law to transform one form into the other one. So power, P equals delta V times I, or delta V squared over R, or I squared times R. So these three formulas can be used, right? Let me frame it. Frame them. Right? And so pretty much nothing else to discuss. So let's just look at a couple of examples, right? And they are conceptual. It should be enough, I think. Conceptual questions 4 and 5, again at the end of the chapter. So let me write CQ. Again, it's a conceptual question, and let's start with the fifth one. So what do we have here? In both actually questions, two resistors, R1 and R2, and the value of R1 is larger than the value of R2. Right? In this case, they're connected in parallel. We need to compare powers. In the second case, in question 4, they will be connected in series. And again, we will compare their powers. Right, some reasonably simple questions. Okay, let me draw first situation. So we have, of course, a battery, right? And then we have two resistors. I think this one, yeah. So delta V and R1 and R2, right? And again, what we know that R1 is larger than R2. So we need to compare powers. Dissipated in these resistors. Of course, you know that the resistors you will feel warm if you touch them, right? That's the power we're talking about, right? Okay. So let me write over here. So P1. No, you know what? Let's first make a decision which formula is better to use. Right? Again, you can use any of them, right? But some of them, one of them will be easier to use than the other two. Because if you try to use the other two formulas, you will have to make one additional step and use Ohm's law. why would you make an additional step if there is a easier way? Okay, let's start, for example, with delta VI. What's wrong with using this formula? Actually, nothing wrong. It's just, again, as I said, you will have to make additional step. Delta V across both of these resistors are the same. Right? So it's good. Delta V is the same. But current, we don't know. And since we have here junction point, of course, current I1 and current I2 are different, right? And we don't have immediately information about that. Of course, you can get that using Ohm's law, right? But again, it will be additional step. Why would we make additional steps, right, if we can avoid that? So this is not the best because we don't have information about current. Then this delta V squared over R. We have information about R's, which is good. But the same problem with delta. But with delta V, actually this is the best one. This is the best one. Yeah. And about this I squared times R, again the same problem. We don't have information about I, current. Information about R, yeah, we do have. Right. So it looks like this is the best option. Right. Okay, so let's try to use it. So it will be delta. And you know what? Also, I need to mention that, of course, delta V1 equals to delta V2, and it is equal to delta V, potential difference across the resistor, or across the battery, because these two resistors connected in parallel, right? Obviously. So now, as a result, I don't use subscript next to delta V, right? I'm using this formula. Delta V squared divided by R1, and for the second resistor it will be delta V squared divided by R2, right? Okay, so delta V's are the same, and of course since R1 is larger than R2 and R1 is in the denominator, so it means that P1 is going to be larger than P2. Okay, so P1 is smaller to me. Since R1 is larger, then of course P1 is smaller than P2. Right. Okay, I just wanted to play with these formulas, right? Kind of making a decision which one is better, right, to use. Okay, and the conceptual question 4. It's a similar situation, but now resistors connected in series, right? Okay, let me draw it. Alright, so this will be a battery and two resistors, right? So the first one and the second one. Distorted slightly. Okay, it's fine. So again, potential difference across the battery delta V, resistor R1 and R2. And again the same. R1 is larger than R2. R1 is larger than R2, and again immediately from the circuit we see that in this case, since resistors connected in series, current is going to be the same. Conservation of current, there are no any junction points, current is the same. So I1 equals to I2, and let me just label it just as I. Current I. Okay, and now again, let's make a decision which formula, which is the best formula. With this form, delta VI, I is the same. Cool. Delta V, of course delta V will be different. Delta V1, delta V2, right? Again, we don't have immediately information about delta V's. Of course you can get it, but of course you will have to make an additional step using Ohm's law. Why would we want to make an additional step? So, it's not the best. Again, it's not wrong, but it's not the best. Then, this, delta V squared over R, the same problem. We have information about R, it's good. Delta V, again, delta V1 and delta V2 will be different, right? And of course, right now, they're not known. Of course, we have to make additional efforts to find them, right? Again, no, it's not the best. Again, it's not wrong, it's not the best. Now, I squared R. We have information again about R's, and I exactly the same, right? So this will be the best because you know immediately information about both of these quantities, right? So now we will use that P1 will be equal I squared times R1, and again you see I don't use any subscripts next to I because currents are the same, and here P2 equals to I squared times R2. And now, since R's in the numerator, and R1 is and R1 is larger than R2, then of course P1 is larger than P2. So it should be enough. Pretty much you can use all those tools which we developed before to analyze circuits, and then on top of that you just need to add one of these formulas if the question is about power. Right? Okay, so it should be enough about power, electric power. Right, let me check if I mentioned everything. Yeah. Yep, that's it now. RC circuit. Right. Continue. We haven't finished one example in the lecture. I will continue tomorrow. And today we will discuss the other situation. So, what's so special about RC circuit? Why do we want to discuss it? The major point. Up to this point, all our currents in all our examples, currents were constant in time. And this is RC circuit. It's the first example, first circuit where current changes in time. And not just current, charge, potential difference, everything will be is or are functions of time, right? So that's the major difference between RC circuits and all these circuits which we've been discussing so far. Okay, and of course there are two situations. Capacitor. First, let's say it's empty. And that's the case which we started discussing in the lecture. Empty capacitor. Of course, you need to use the battery in order to charge it, right? So of course, if you connect battery directly to a capacitor, okay, it's not a good idea because the current will be very large and high chances that you can damage your capacitor. So of course, it's not a good idea. So it's better to slow things down to reduce the amount of current by putting a resistor between them. Right? So you have a battery, resistor, and a capacitor. So that's the case of charging a capacitor. And again, that's what we started discussing in our lecture. Here we're going to discuss the second case. What if capacitor is already full with the amount of charge Q0, right? Let's say Q0. And then you want to drain it. And of course, how can you drain it, right? Through the resistor, because if you just connect negative electrode of the capacitor to the positive electrode of the capacitor, right? Again, you can damage just the system. Current will be too large, and yeah, it's better not to do it. So it's better to drain it through a resistor. Of course, now in this case, battery is not needed. You have capacitor full of charge, so now you need to drain it. You don't need a battery, right? So now we have capacitor fully charged, and we want to drain it through that resistor, right? And so what's the situation? So at the initial moment of time over here, there is a switch, maybe charge is full, the amount of charge initially Q0, right? And then at the initial moment of time you close switch, and of course current will be, okay, we will get it, but most likely it will be also large, right? I0. And then what we want to know, if you look at that circuit at any moment of time later, what will be the amount of charge at that particular moment of time in the capacitor? And what will be the current flowing through the resistor at that particular moment of time? So you know initial conditions, you want to know Q and I at any moment of time later, right? Because everything changes in time. Okay, so now let's discuss the situation. Analyze, not just discuss, analyze it. So these are our questions, right? And what can be used? Kirchhoff rules, no limitations, right? Of course, a junction rule is not applicable here because we don't have junction points. So we have to apply only loop rule. Okay, so let me write down. So loop rule, right? Okay, in order to apply loop rule, so we need to draw some additional lines. So first of all, current. In this case, we don't have to guess, we know current direction because we have only one capacitor. This is, let's assume, positive electrode, this is negative electrode. So current will flow from plus to minus. So this is current, and again, you remember, it's a function of time. Everything is, basically right now I'm drawing this circuit at this moment of time, at an arbitrary moment of time t, right? Okay, then charge, of course, charge in the capacitor will be over here, right? Charge, it's a Q as a function of time, right? And of course we need to choose a direction, travel direction for the loop rule. So let's assume that this is my travel. Okay, so all preliminary steps are done, and now let's write down the equation. So first, potential difference across a capacitor. Is it positive or negative? Look, we travel, you see, that way, clockwise. So first, we are here, that's initial point, negative electrode, final point, positive electrode. So V plus minus V minus, potential difference across a capacitor must be positive. That's why I put here a positive value, plus delta V sub C. Then we cross the resistor. Travel direction down, current direction down. Rule number 3, the previous recitation class. Contribution minus IR, right? When directions are the same of current and travel in the resistor, contribution is negative. So minus IR. Okay, and that's it. There are only 2 elements. But we need to write explicitly what is inside of delta V, what can be used. Let me write, so we can use just the definition of capacitance, Q over delta V sub C. Right? So that's delta V sub C, it's a Q divided by C. Yeah. Okay, so as a result, Q, which is the function of time, divided by C minus I times R equals to 0. So it looks like this is the equation we can get. How many unknowns do we have in this equation? Look at the question which we want to find, quantities which we want to find. Q, it's this, and current, which is this. 2 unknowns, 1 equation. It doesn't sound good, because mathematically it's not solvable. But of course, with your gut's feeling, you must feel, right, that current and the charge, they're connected. They must be connected, because this current, what's the origin of this current? These charges escape from the capacitor and creates that current. They must be connected, right? So let's connect, let's find the relationship between current and the charge. Okay, so let me write, so 2 unknowns, and I put a big set face, right? Okay, so now I will put a bullet and I write connect I and Q. So let's connect charge and current, charge and current. Okay, so in order to connect, let me draw this part of the circuit. Let me over here, sort of this part. Right. I just want to follow the charge, and I just want to draw this. Okay, let me draw it here. So let's say this is our capacitor. This is the wire, right? Okay, that part of the circuit. And what is? Let me write. So Q small. It's a charge. I denote that way. Charge in the wire. When the charge is in the wire, I can use Q small. It's a charge in the wire. And of course then, how can I write current? Current in the wire. Definition of current, dq over dt, Q small. Because that's how we denote charge inside of the wire. So I equals dq over dt. Right? Okay, and now let me draw this definition of current on the picture. Right? So what is basically, how do we measure current? You pick a cross-sectional area across the wire, right? And you sit there and measure the amount of charge crossing that cross-sectional area, which is dq. And that happens over the period of time dt. And let's say this is the amount of charge dq which cross that cross-sectional area. So that's what by definition you have to remember, like 4 lectures ago we defined current dq over dt. But again, I want to connect this q in the wire with the charge in the capacitor, which is q capital over here, right? So this is q capital. Okay, so now this charge dq in the wire, where was this charge a few moments ago? Where was this charge a few moments ago? It came from the capacitor. It was here, maybe millisecond, maybe microsecond, maybe picoseconds ago, right? So this charge was here, right? So that was this dq, and it ran to the wire. Okay, so the amount of charge dq ran away from the wire, from the capacitor. So what happened to the charge inside of the capacitor? It went down, right? I know if 5 people ran away from the room, right, the number of people in the room goes down by 5 people, right? Simple logic, right? So let me write. So dq, okay, ran away from the capacitor. So as a result, I can write the charge in the capacitor. Q final equals Q initial. So this is before dq ran away, and that is the final. Of course, Q initial minus dq. Right? Simple logic. This is smaller because this number of people ran away. Okay, let me solve it for dq. So dq goes to this side, q final goes to that side. It will be q initial minus q final. Right? Okay, so that's simple logic. 5 people went away, so as a result, number of people becomes smaller. Right? And now let's recall from the definition from the other side. From the other side, what is by definition dq, change in the charge in the capacitor? Just forget about all this. Just by definition, like delta. What is delta? It's a final value of something minus initial all the time. D delta, it's a final value of something minus initial value of that something, of that quantity. So from the other side, of course, dq equals to q final minus q initial. Now let's compare these two things. dq small, q initial minus q final. dq capital, q finals minus q initial. So how can we relate this? Through the minus. dq small equals to minus dq capital. So as a result, I can write so dq small equals to minus dq capital. Almost done, right? So now as a result, we can use this in the definition of the current, and we connect current in the wire and charge in the capacitor. As a result, I can write, so I'm just rewriting this using q capital, so it will be minus dq over dt. So we will frame it, right? And it's very important, it's this relationship. We will need it. Usually book doesn't go into this. Book usually says, it's obvious that current in the wire increases at the expense of the capacitor, charge in the capacitor. As a result, I equals minus dq over dt. Whenever I read it, I'm not happy about it. Not completely happy, right? Again, it's a gut's feeling. Yeah, I feel it must be correct, right? That statement, it's correct. But every time I felt like I want to develop something more rigorous to show that that is true. Okay, so I developed this derivation discussion, no, the discussion, yeah, basically derivation. How to connect current in the wire and the charge in the capacitor, right? Okay, so now back to our equation, right? Okay, let me sort of frame it. I will put small bullet and back to our equation, back to this equation. So, but again, instead of current, I can use minus dq over dt. So I'm just rewriting q over c minus this minus from the formula, this minus from this formula, minus dq over dt and times r equals to 0. So now we have only one unknown charge in the capacitor. That's what we wanted. Again, that was the trouble with this equation, two unknowns. Now it's just one unknown. Okay, now it's a simple first order differential equation, right? At this point you should be able to solve these differential equations, right? But you're taking different level of calculus, right? So now at this point we just need to make it look nice. We just need to combine q's together, right? So let me just move around. Minus and minus give us plus. And I'm going to divide the whole equation by r, because I don't want to have this r in front of this derivative, right? So as a result I will get dq over dt equals plus q over rc equals to 0. So again, I divided this term by r, so as a result this is free of any factor. And this q divided by c and divided by r, it will be rc downstairs, right? q over rc. Okay, obviously again we're getting rc constant. Let's label it. Let's denote tau equals to rc, rc time constant. It can be shown that it has units of time, right? And so now this can be solved, right? We need to separate just variables, combine q together, right? So let me rewrite it. So it will be dq over q equals to minus dt over tau. Okay. And I just want to write the limits. Now we have to integrate it, and I want to show the limits. What's the initial value of the charge? Lower limit q naught. The final amount of charge, that's what we want to find, qt. Q at the moment of time t. And of course integration over time from initial moment of time when I close the switch to the moment of time, this moment of time when we discuss the moment we discuss this circuit at that moment. Alright, okay, so of course you can integrate it. I'm not going to do it, right? If you know, alright, it's very easy. If you never integrate it, okay, it's not the best, but at some point you will learn it. So now we can solve it, and it will be q as a function of time, q naught, and e to the power of minus t over tau. That's the function. That's the function which we wanted. So that's how charge in the capacitor changes in time. Okay, we can plot it. Right? If you plot it, okay, I will plot it here. Time. And here charge. Of course, for the exam you don't need this derivation, but during this derivation there are plenty of physics which can be discussed, so I decided to do it, right? And so far I cannot convince myself of skipping it, because just writing down this formula, that's for general physics, okay, but for engineering departments it's better to discuss that. Okay, so what? Q naught, it's initial amount of charge. It's here somewhere. Let's say this is Q sub 0. You see this point? And then it decays exponentially. Something like this. And what's the value of tau? Tau, it's a certain moment of time. It has units of seconds, right? It's a t at a certain moment of time. So what happens when t equals tau? So if t equals tau, you will have minus tau over tau, it will be minus 1. So e to the power of minus 1. E to the power of minus 1 is like a e in the denominator. So if you calculate 1 over e, which is 1 over 2.7, it will be approximately 0.37. Right? So now I can show that over here, if t equals to tau, then amount of charge, that point, it's 0.37 q naught, 37 Q naught. It's basically the moment of time when the amount of charge reaches 37% point, right, of its maximum value. 37% of its maximum value. Okay, charge reaches 37% of its maximum value. So that's what happens at tau. Now then, next, so now we know how charge changes. How can we find current? How current changes in time? That's our second question. Right, so I will put a new bullet. So I as a function of time. So what can be done to find this? And that's why I spent all this time connecting current and the charge. And they're connected to the minus. When you charge the capacitor, this relationship with the plus. But when you discharge the capacitor, this relationship with the minus. So now we have to put minus dq over dt. Basically, we just need to differentiate this. Minus dq over dt. So differentiate this. If you differentiate, you will get I naught e to the power of minus t over tau. I'm not differentiating, right? Because yeah, you can do that by yourself, right? And it will be, of course, in my notes, right? In lecture notes. Okay, and then you can ask additional question. What about, for example, potential difference across a resistor? And of course, the same potential difference will be across the capacitor. So how can we find potential difference across the resistor? It's a very, very trivial question, because now we know current. If you multiply current by the resistor, the value of the resistor, R, that will be the potential difference, right? So the last question, right, so delta V across the resistor, it will be I as a function of time times R. And of course, yeah, if you plot, for example, current, it will have again similar plot. It will have an exponential dependence, right? So again, if I plot I versus time, again it will be exponential drop, something like this. Okay, so that's what I wanted to discuss, kind of, yeah, derive. And problems are much easier. Problems usually is about just using these formulas, this or that or that. So there are two types of problems. It's basically a function, and we all know how to deal with functions, how to work with them. The first type of problems: time is given, find the amount of charge at a certain moment of time, at that moment of time. Or reverse situation. Let's say charge is given at a certain moment of time, find that moment of time. Right? Sort of problems of that type. And again, as I noticed, usually students are quite comfortable with problems like this on the exam. Okay, so I think I need to erase this because I need that space for problems. So problem 35. Okay, I want to save that heading. Okay, so chapter 28. 28 and problem 35. So we have RC circuit discharging this case. Again, be careful, right? If you see the problem on the exam, on the test, okay, make sure that you use the right set of formulas, right? Because there's a charging situation, again, that will be discussed in the lecture, and now we discussed discharging. Okay, so we have discharging C. Again, C is a capacitor. And what is given, you know what, I will probably even quickly sketch, of course, similar picture, right? So that's our cap. It is drained through that resistor R This is C. So the value of C is 10 microfarads. Resistance 1 kilo ohm. That's what is given, and now again at the initial moment of time the charge, the capacitor is full, right? And actually that charge is given. Okay, I almost missed it. Q naught is 20 microcoulombs. Okay, so the situation again. Initially this capacitor is full, 20 microcoulombs, and then you, at the initial moment of time, you close the switch, and of course it starts draining, right? So of course this charge becomes smaller and smaller and smaller and smaller and smaller, like this. So we need to find the moment of time when charge becomes 10 microseconds. Right. Okay, let me write that. So what we need to find, let me label that moment of time as T1, and I will write when, which way I wrote, when a charge at that moment of time, let me just label it Q1, just for simplicity, right? So let me just label it Q1, equals to 10 microcoulombs. Basically, the amount of charge is dropped by a factor of 2. Initially 20 microcoulombs, final 10 microcoulombs. We want to know that moment of time when charge gets halved, right? So let me first show graphically what we need to find, and then mathematically. Right? Graphically, okay, let me separate this. So graphically, it's that's how a charge changes with time. Okay, that graph. So this is Q naught, and then it decays, right? So this is Q naught, which is given 20, and then what we need to find? We need to find some moment of time. So this will be our Q1, which is half of that charge, right? And we just need to find this moment of time T1. That's what we need to find on the graph. Mathematically, so that's how a charge changes in time. So we just basically, we know this, the final the amount of charge at a certain moment of time, and we need to find that moment of time. Just work with the function. Right. So Q naught e to the power of minus t over tau. So that's what we need to use, right? And so if we apply for our moment of time which we want to find, so it's a Q at T1, which is Q1, equals Q naught and e to the power of minus t to the T1 divided by tau. Right? So I just apply this formula for that moment of time T1 which we need to find. What do we have to find in order to start massaging this formula? What is still missing? So this is given, this is given. That's what we need to find, tau. We need to know tau, right? Tau is R times C, and since resistance and capacitance are given, so we should be able to find RC time constant easily, right? So tau equals to R times C. R is 1 kilo ohm, 1 times 10 to the power of 3 ohms. C, 10 micro farad micro, 10 to the power of negative 6. 10 to the power of negative 6 farads. So what? Here 10 to the power of minus 5, power of 3, negative 2, 10 to the power of negative 2. Right? 10 to the power of negative 2 seconds, which is 0.01 seconds or 10 milliseconds. Right, so whatever you prefer. 1/100th of a second or 10 milliseconds. Okay, so now we're all set. We know tau, so we just need to solve it for t. We just needed to solve it for t. So, no, this is our formula. So let's just massage it a little bit. Basically, we need to just turn this equation inside out. Right. So first I'll take q naught to this side. So it will be q1 over q naught equals to minus e to the power t1 over tau. Then our unknown is in the power of this exponential, right? So how can we drop this power? What can be done? We need to take natural log of both sides, right? You remember high school stuff? I hope it was in high school. At least in my time it was in high school. Alright, so if you take a natural log, of course it will be natural log of q1 over q naught equals to minus t1 over tau. Right. And so now we just need to get t1. So will be t1, tau goes up here, minus also to that side, so it will be minus tau, a natural log of this ratio, q1 over q naught. You know what? Again, another small minor compulsion. Whenever I see minus, they make me feel nervous, uncomfortable. So whenever I see them, I try to hide them somewhere. Of course, legitimately hide them. And we can easily hide them. How? What should we do in order to get rid of this minus? Property of a log function, natural log. Right. Okay, let me remind you. Right over here. Okay, let me use different color. So if you have, for example, minus natural log of x, it's like the same as natural log of x to the power of minus 1, which is natural log of 1 over x, right? So it means that we can take minus over here, right? So it will be to the power of minus 1. And this ratio to the power of minus 1, it's like flipping this ratio, right? So let's do it. We can get rid of this minus and flip this ratio. It will be q naught over q1. Properties of log functions. So as a result, we'll have tau times natural log of q naught over q1. Done. So that is the formula. So now we just need to plug numbers. So let's do it. It will be t1 equals tau is 0.01 seconds, and natural log of 20 over 10, it's 2. 20 microcoulombs divided by 10 microcoulombs, natural log of 2. You can easily calculate, right? So you will get, let me check my notes, 6.9 milliseconds. Right. So that's at this moment of time, the charge is reduced to 10 to microcoulombs, from 20 microcoulombs to 10 microcoulombs. So it gets reduced by a factor of 2. Okay, I decided to add. Basically, this is the problem, but I decided to add 2 additional questions, and I need to find space where I can write them. We still have a few minutes. Okay, let me erase this part. Yeah, let me erase over here. So let's find, for example, how potential difference across what? Okay, maybe let's find current. So what about current function? How can we find? So let me put additional questions. Additional questions. So how can we find current? in this case, a function. Again, it's a discharging situation. We just derived it, right? And you see the relationship between charge and the current, again, through this minus, right? So here I explained this. So we can just grab our function, differentiate it, and we will get what we want. So it will be minus dq over dt, right? So it will be minus d over dt, and our charge is here, right? So it's a q naught e to the power of minus t over tau. If you differentiate this function, okay, q naught stays, and after differentiation minus 1 over tau will pop up, right? So it will be minus q naught, then times minus 1 over tau, and e to the power of minus t over tau. Right, minus minus give us plus. Right, and then q naught. And what is tau? Tau by definition is r times c. You know what? At this point, no, I don't need to dive into r times c because we know tau. We found tau to treat somewhere here. Right? We know q naught. We know tau. Right? We can get the function. So q naught is 20 microcoulombs divided by tau. Tau is 10 milliseconds, right? Times e to the power over t over tau. So it will be 2 amps. Oh, yeah, milliamps, because here we have micro, it's a 10 to the power of minus 6, downstairs 10 to the power of minus 3, so it will be 10 to the power of minus 3 will stay, right? So it will be 2 milliamps e to the power of minus t over tau. Okay, yeah, I can erase this. Right. And then, for example, we can also find, for example, potential difference across the capacitor. What can be done? Or potential difference across the resistor. It will be the same because this potential difference and that potential differences are the same, right? So you can use either I, which we just found, times R, or you can use delta Q. Oh, okay, where is it? Delta V. Okay, let's just use this. It's easier. I would just thought about using the definition of capacitance, right? There are two ways of finding it. So now let me use first that. So now delta V across the resistor equals R times I as a function of time. Right? The value of R is given. Where is it? 1 kilo ohm. Right? Times that. So it's 1 kilo ohm times 2 milliamps e to the power of minus t over tau. So it will be kilo and mini 10 to the power of 3, 10 to the power of minus 3 gives us nothing. So we have just 1 times 2, it will be just 2 volts times e to the power of minus t over tau. Or, as I said, or it's the same, right? Or delta V across the capacitor equals to, okay, the definition of capacitance, C equals Q over delta V, right? So delta V will be Q over C. So Q as a function of time over C, right? So of course it will be the same. It will be the same. Okay, so that's what I was planning to discuss. In the lecture, I will probably also mention, right, another thing. Just a minute. Here, all the time, we had one capacitor and one resistor. But what if we have more than one capacitor and more than one resistor? So what can be used? For example, let's say we have here 2 resistors connected in parallel. And here we have 2 resistors connected in series. What can be done? Find an equivalent capacitance on this part So introduce C equivalent. Find an equivalent resistor on that side. Introduce R equivalent. And then you have one capacitor, one resistor, find time constant. Exactly the same story, right? Okay, so that's what I wanted to discuss for today, right? Okay, if you have any questions, you can ask, right? Otherwise, I will see you tomorrow. And again, derivation, I just went through the derivation because I felt like there are plenty of interesting physics which can be discussed. But in problems, all the time we just need to use, most of the time we just need to use these functions. Of course, need to remember time constant. And these manipulations, how, for example, to get current from charge or potential difference, right? Potential differences or potential. Okay, thank you. And again, if you have questions, you can ask. Otherwise, I'll see you tomorrow.